So, matter and its classification. We usually classify substances by states of matter, and we're going to talk about those states of matter, solids, liquids, and gases in the next set of notes, okay? But for our purposes today, we're looking more at it from a different perspective. Chemistry is the study of matter and the changes it undergoes, right? So, matter could be anything that we're going to talk about in a minute, has mass and takes up space, but like in this picture over here, you are seeing the wood burning, fire. This is a combustion reaction. Matter's undergoing some changes in there, and it's producing heat, which is kind of cool. Over here with the flowers, definitely you have the leaves. They're undergoing lots of chemical reactions, you know, with the chlorophyll and the making of the sugar. Even the pigments in there, making it pink and so forth, those are chemical reactions giving off certain colors. And here we're talking about just the matter itself. This particular case is liquid, it's milk, it's a mixture, going back into those kind of things. Okay, this is like the generalized atom, although we don't really follow that model anymore, but we'll get into the models of the atom later on in Unit 3. Okay, so matter, anything that occupies volume and has mass. So has mass and occupies volume. We all are made up of matter. On the basis of composition, we divide it into the pure substance and the mixture categories, okay? Which we're going to also investigate over here in the activity. Now you see your flow chart. Kind of went over all the particles are identical. We're going to call them pure substances. If all the particles present are not identical, where you have different types of particles, they are going to be mixtures. And from our Pogel activity, the one that we did with the shapes and the circles, the squares, and the triangles from the other day, we're going to be looking at some of that coding and that system and comparing it to the actual system that we use in chemistry. Elements made up of one type of atom. Okay, that's the one possibility of pure substance. The other one we'll get to in a minute. Pure substance that cannot be separated into simpler substances. In other words, it can't be broken down into smaller particles without changing the identity of that particular element. Like you can break down an element, you can have it undergo nuclear decay, you can break apart the particles, but that actually changes the essence of the element. It's no longer that element. So you can't really break it down further from this point without completely changing the properties and the chemical composition and so forth. So the element is the lowest that you can get, and they're made up of individual atoms or twin atoms. We're going to talk about those diatomics in just a minute. Here, as you see, aluminum foil, that is aluminum directly off the periodic table there. Aluminum metal atoms making up the nice foil that we use for various things. I use it in my kitchen all the time to, cover food and so forth. Copper wire, also copper is pure substance, element off the periodic table. Okay, good conductor of heat and electricity. So they're organized in the periodic table, and you're going to be getting a copy of this later on. I know we don't expect you to memorize the entire thing, but you need to have a good enough feeling of being able to find stuff. Like in the general area where to look for things, okay? But you don't have to memorize any of it. You just need to be able to use the information on it when needed, okay? Lots of different elements, but these are the only ones that have, been discovered or even manufactured in labs. Some of them are synthetic. And they keep adding. This row right here has more on the periodic table in the back there. But they keep adding as they keep trying to find and discover new elements. Okay? Now, Now, going back to that coding thing and making sure everybody's paying attention to the codes, okay? So this is kind of a little bit more detail I wanted to talk about. The symbol is 1 or 2 letters. The first letter is always a capital, okay? Second letter, if there's a second letter, is going to be a lowercase letter, okay? So, for example, potassium. Some of the letters actually match their name, some of them don't. Like potassium is K. That's because it's from some kind of Latin root word. I don't exactly remember what potassium is from. But like tungsten is W, and that's from wolfram, and wolfram is like a Latin word or a Greek word. It's something like that. Calcium, though, is very good because it matches its name very easily. Carbon matches its name. So you got to just be careful, like gold. Gold isn't G. Gold is AU, okay? Silver isn't S. It's AG, okay? Argentium, I think is what it's from, the word. So keep in mind that some of the element symbols match their words. Some of them, they're their names. Some of them don't, okay? Now, going back over the monatomic elements, these are the ones that are made up of single atoms. Only one particle in it. Over here, the diatomics, and there are only 7 of them, and you're going to eventually have to memorize them by the end of Unit 3. Okay? Diatomics are the twin ones. They don't exist in nature by themselves, like oxygen. We breathe in O2. We don't breathe in O. We breathe in O2. Okay? And I'm going to show you a few little quick systems, and we'll revisit this later. Making sure those are in there. For the diatomics, some people like to use this, and you can write it down now just to get it started. Dr. Brinkelhoff. Anybody see how that could be a nice little system to remember them all? DR is going to tell you it is bromine. I is going to tell you it is iodine. N is going to tell you it is, well, you got to know N. Nitrogen, there you go. Cl, what's Cl? Chlorine. H is, come on, H. Hydrogen. And O, the easiest one of all, because I've said it multiple times, is oxygen. And last but not least, what would F be? Well, it's fluorine. Fluoride is the ion version of fluorine. They put that in our water, and it's good for our teeth. But fluorine is actually F2. Fluoride is going to be a little bit different, but it is still made of essentially a fluorine atom. Okay? So Dr. Brinkelhoff is one way to know your diatomics. Another way to know, and we'll go over this more when you get your periodic tables, but we call it the 7 rule. Start at 7 because nitrogen is 7 on the periodic table, and then it makes a 7. So like oxygen's here, fluorine's here, chlorate's here, bromine's here, iodine's here. I don't know if you can see that up there on the periodic table. It starts at 7, it makes a 7. Now, out of that though, because this would be 8, this would be 9, and then going down. So start at 7, you make a 7. But then you have to remember hydrogen is the 7th because it's all the way in the upper left corner. Okay? So there's that possibility when you get your periodic tables. If you're more of a visual spatial thinker, this way might be better for you. If you're more of a wordy person, you might like the Dr. Brinkelhoff version to have how to memorize them. Because there's only 7. The rest of the table is all monatomic, single atom elements. Okay? So keep that in mind. Now let's talk about compounds made from 2 or more types of atoms. The thing we need to talk about here is that they are chemically combined. They have a chemical bond, whether it's an ionic bond, a covalent bond. You've heard of these things hopefully from physical science. It has some kind of bond, some force, glue holding it together. The other interesting thing about compounds that we should note, and I think it's on your paper there. Well, they can't be separated physically, so you can't evaporate out part of it, or you can't filter out part of it, whereas you can do that with mixtures. The other part is the properties. The properties of the compounds are not always the same as the elements themselves. Okay? For example, let's look at sodium. Is anybody familiar with sodium? Yes.
It explodes.
In water. It explodes in water. That's exactly accurate. So sodium is an alkali metal. It's that first group of metals. They're very reactive. Okay? And they're very soft. They look lustrous, though. They look shiny, just like a metal should. Okay? But they're very soft. And in order to keep them from reacting with air, you have to like keep them submerged in oil so that it doesn't react with air. That's elemental sodium. Yes?
So what happens to it?
It forms a coating on the outside. It's like a white coating, or no, is it a black coating? It's a type of rust. Remember, just the red stuff that you see like on your bicycle and stuff, that's the iron rust, the iron compound rust. But lots of other metals form rusts that are, could be white coating. It could be a green coating. I'm sure you saw, on the Statue of Liberty, the copper turns green. That's the rusting of the copper. So rust can be in different types of fashions here. But so sodium, elemental sodium is really reactive. You need to keep it submerged in oil and so forth. Now let's look at another element. Does anybody know what that is? Well, it's in a flask. It's filling up the container. Close. It is a gas. It's actually chlorine gas. Chlorine gas is yellow. Okay? You don't want to breathe it in. It's very toxic and bad for you. I'm not sure. I'd have to look that one up. However, you wouldn't want to breathe that stuff in. But if you took the sodium and the chlorine and you put them together, what do you get? NaCl, or salt. Yeah. And we like this stuff because it tastes good on our food, right? And it's not toxic to us. And it's not reactive and explosive and stuff. Well, I mean, yeah, you don't want to, you're exactly right. Everything in moderation. Anything could be toxic in a large amount. That's true. Even water can be toxic in great amounts. Okay? So, but you wouldn't want these elements separated. You wouldn't want to be exposed to them separated. But as they're together, glued together as a compound, they're very useful, not just for food, but it's also good as a preservative and things like that. For not just ingesting it, but for other things too. Okay, it's good for melting the ice in the wintertime. There's lots of good uses of salt. Okay. So the properties are different than the properties the elements are made of. So we have this reactive sodium, this toxic gas, turns into this very white crystallized stuff, okay, that doesn't have those properties at all. Contains more than one capital letter. So remember the coding from the POGL. You had your R, S, Q, 2, T's or whatever, right? Same idea here. You have your capital letters. Okay, 2 or more capital letters indicates 2 or more elements. 2 or more capital letters, 2 H's, or H and an O there. The NaCl tells you that that's 2 separate elements. This one's actually hydrogen chloride gas or hydrochloric acid. And this one we would call sulfuric acid, and it has hydrogen, sulfur, and oxygen in it, making it a compound. Okay? So getting specific into the coding, and this will also help you with the activity that you're about to do. So pay attention to that coding. 2 or more capital letters will indicate to you you've got 2 or more elements in there, so you know it's going to be a compound, right? Also, as you saw, based off of your pictures, you need to be able to recognize the circles and see that these ones that are shoved together like that, that means this is a chemical bond. So you know that's, and they're different shapes and different colors, so you know they've got to be different elements. So you would be able to look at this picture and identify it as a compound. Okay, just like we did on the previous lesson with those pictures. Same idea here. Okay. Now for the mixture side of things. Quick review. Combination of 2 or more pure substances. So it could be elements mixed, it could be an element and a compound mixed, or it could be two compounds mixed. Lots of different ways to do mixtures here. You can separate them physically, and we're going to do a lab on separation techniques like filtration, distillation, chromatography, and evaporation, and like magnetism. You know, something that is attracted to magnets, you can use that in order to separate from something that doesn't have that property of being magnetized. So there's lots of different ways to separate things. But we need to talk about the uniform composition ones. They have the same, or they're uniform. They're homogeneous. They could also be called homogeneous, and they could also be called solutions. Those three things are interchangeable. But it means when you look at it, you know there's two or more things in there, two or more pure substances in there, but everything looks uniform, like Kool-Aid. You look at it, it looks like a nice colored liquid. But we know there's sugar in there, we know there's flavoring in there, we know there's water in there. So there's a bunch of things mixed together. Okay? But can you tell which one is the sugar molecule and which one's the food? No, you can't. So that would be a homogeneous mixture, a solution. Okay? The other type is the heterogeneous. Heterogeneous ones are not uniform. Okay? You can pick out the particles. You can see the differences in there. Like sand and water. If it's nice and cloudy like that, eventually the sand would separate to the bottom for you by particle size and density. And then you can decant or pour off the water at the top. So that's some separation technique idea there. But you should be able to pick out that it has, you know, different things in there. You would be able to tell if it layers out and so forth. Okay? So, mixtures with uniform composition, aka solutions, also know that. Example is salt water. You can't pick out the salt from the water. Okay? All mixed kind of evenly. You don't see the difference. Heterogeneous, no uniform composition. Individual substance remain distinct. And sand, water, but you'll see some more examples in the activity. Okay? And you can see in this pictorial representation, this one's a compound. These are individual monatomic elements. Okay? So as you're recognizing the pictures here, being able to tell. And here's a couple more examples. What is this a picture of? Anybody know what that is? This guy? It looks like granite, yes. So we're going to go with granite. You can see there's like the black specks, the white, there's different color minerals in there that they've all been mixed together. You can see. This being apple juice. You know apple juice has got sugar in it, it's got malic acid, it's got a bunch of different things, the apple flavoring in there. I don't know exactly what the chemical name of the apple flavoring is, but it looks kind of like a light brown or orangey liquid, but you can't really tell where the particles are, so that would be a solution or a homogeneous mixture.